All right, I'm back and I'm going to continue to explain the modified Atwood's machine problem with friction. What we left off with was we created net force equations for both the A and the B blocks. And I've erased some things so I can make room to do some math here and actually calculate what the acceleration of the blocks are going to be. So I'm going to start off by noticing and reminding you that the tension forces are equal because of Newton's third law, which are highlighted in pink, and the accelerations are equal because this system of objects is moving with a constant acceleration and they are tied together, and so that acceleration must be the same, or else we're going to have a situation where the string is breaking or bunching up, and that's not really going to happen. So now our next goal is we want to calculate what the acceleration is going to be. And we have a system of two equations. We could do a couple different things to solve this, but what I'd like to do is to do substitution method. So because I'm looking for acceleration, I'm going to solve for the tension with the blue equation. So Ft, I'm just going to add friction on both sides. So I have mass of the A block times the acceleration plus the force of friction. And now that I've solved for Ft, I can plug that Ft into this Ft. And when I do that, I will eliminate the Ft's, the tensions, and then I'll just be left with one unknown, which is my acceleration. So I'm going to go ahead and do that. I'm actually going to do it over here. So I have Fgb minus, and now I have the tension, which is going to be the mass of the A block times the acceleration plus the force of friction on that A block, and then that's all going to equal the mass of the B block times the acceleration. So now I need to solve for acceleration. I need to collect my like terms. I need acceleration to be together, so I'm going to bring mass of A times acceleration over to the right. So I have Fgb, and then I'm going to add ma times a on both sides. So then I have plus ff is equal to mba plus maa. Now, the next thing I'm going to do is if I want a by itself, I'm going to pull it out of both of these masses. This is I'm kind of pulling it out because if I were to factor it back in, I guess I'm factoring it out because if I FOIL it back in, it would be the same thing there. And then I just have Fgb plus Ff. Then I can divide both sides by Mb over Ma. So I have Fgb plus Ff divided by Mb plus Ma is equal to the acceleration. Now I just need to plug everything in. The only problem though is, and we have to do, this was a little bit of math, but now we have to do a little bit more physics. What is our Fgb? So the way that we get Fg is we use this equation. The force of gravity, or the weight of an object, is equal to the mass times g, which is the gravitational field strength. So Fgb is just going to equal the mass of B, which is 0.2 kilograms, times 9.8. And when I do that, I get, sorry, just want to make sure I'm right. I'm not really good at mental math, so 1.96. So that's what's going to go in for Fgb. The other thing that we just learned is that we have a force of friction equation, which I'm running out of room for. Let's see, I guess, write it up here. Sorry, I'm out of order. So the force of friction is equal to the coefficient of friction times the normal force. Well, we have the coefficient, that's 0.2. But we don't have the normal force. But if we go back and look at our picture, you can see from our equation here, or not our equation, our blue force diagram, that the force of gravity of A is equal to the normal force. So if we can find the force of gravity of A, FGA, then we'll know what the normal force is. The force of gravity A is actually just going to be the mass of A times G, right? And G is 9.8 and the mass of A is 0.6. So when I multiply all three of those things together, I should get my force of friction, which is 1.176. 1.176. So now I have my FGB, I have my force of friction, so I can literally just plug those in. So that's going to be, let me use the right colors here. So we have 1.96 plus force of friction, which is 1.176, and then that's all divided by the sum of the masses, which is the mass of B is 0.2, the mass of A is 0.6, and then that's equal to our acceleration. So 1.96 plus 1.176 divided by 0.8 is going to give us an acceleration of 3.5075, and if we put this in 2 sig figs, we get 3.5 meters per second squared, and that is our acceleration of the block. You would think that that's it, right? Because we got the acceleration, we're all done, but that's not entirely true. We actually now need to find out what is that tension going to be. Luckily, though, we have two perfectly good equations here that will tell us what that tension is. And now that we have acceleration, we can actually just plug it back into either one of these equations to determine what the tension is going to be. So I'm actually going to pick this equation right here, see if I can memorize it, because I'm going to do a new one here. So Ft equals ma times a plus ff. So Ft equals, ma times a plus ff. And now that we know that the acceleration was 3.5, we know the force of friction was 1 point something. Let me go back and just check it. It was 1.176 newtons. And we know the mass of A was, that one was 0.6. So now we just plug it all in and solve for Ft. Easy. So Ft equals 0.6 times 3.5 plus the force of friction, which is 1.176. 0.6 times 3.5 plus 1.176 gives us 3.276, which is approximately 3.3 newtons, and that's our final answer. And so that's how we break down a friction modified Atwood's machine problem to solve for the acceleration and the tension. I hope you learned something.